We live in a world we think we already understand. A world built on unbreakable laws. Light moves at a fixed speed. Gravity always pulls you down. And most importantly, time only moves forward. These are the fundamental, unquestioned truths that define who we are and what we call reality. But there are places in the universe that don't just break these rules. They erase them. These aren't just cosmic objects. They are monsters that feed on light. They are black holes. We're used to thinking of them as giant vacuums that suck in matter. That's way too simple. If you think a black hole is just the end of the road, it means you haven't looked deep enough. Because its true, horrifying heart is hidden inside the most impossible concept the human mind has ever tried to grasp: the singularity. Think of any object you know: a star millions of miles across, a planet weighing sextillions of tons. Each one holds a finite, measurable amount of matter. Now imagine all those billions of tons crushed, not down to the size of Earth, not down to the size of a grain of sand, down to a point that has no volume at all. That's not a metaphor. That's the scientific description. To even begin to feel that density, we need an analogy that makes your head hurt. Take our solar home, our sun. It weighs about 2 nonillion metric tons. That's roughly 4.4 quadrillion pounds. Now imagine you don't just take our sun, you take a billion suns like it. That's how supermassive black holes and galactic centers work, and you crush them. But you're not just crushing matter, you're crushing space itself. Our laws of physics, which work beautifully on Earth and our solar system, even across other galaxies, fall apart here. At the singularity, the point at the center of a black hole, density becomes infinite. Gravity becomes infinite. And that infinity isn't just a very big number, it's a wall. But the most terrifying part isn't about space, it's about time. When you look at a clock, you see the hands move from past to future. Inside the singularity, there is no past and no future. There is no where and no when. Space and time, the axes we treat as absolute, simply stop existing. Every direction, up, down, forward, backward, collapses into one single direction, into that infinite, sizeless point. That's what makes a black hole not just a monster, but an anti-universe. What if you could somehow be there? What would it feel like to stand in a place where your entire reality, your personal history, all the physics that ever held you up collapse into nothing? That question has been haunting physicists, astronomers, and even philosophers for almost a century. And to get even a little closer to an answer, we first have to understand its boundary. We have to understand what the event horizon really is. We started with a question that lives beyond physics, at the center of infinite density. But to understand that invisible center, we first have to look at its edge. That edge is the event horizon. A lot of people think a black hole is just emptiness, some kind of cosmic pit. But it's not. It's a place where gravity takes the law of light and simply cancels it. The event horizon isn't a solid wall. It's an invisible but absolutely unbreakable threshold. Crossing it means saying goodbye to the rest of the universe. To understand this point of no return, forget the equations for a moment and think about a river. The entire universe is built on a structure we call space-time. Think of it as a gigantic river. Most of the time, this river flows smoothly, slowly. Light is the swimmer moving through it at the maximum speed we know, about 186,000 miles per second. In that kind of current, light can easily cross the distance from Earth to the Moon in roughly a second and a half. But when this river of space-time curves around a black hole, it starts to tilt downward. Gravity there is so immense that it literally stretches space. The closer you get to the center, the faster that current becomes. And that's where we reach the horizon. Imagine you're swimming in that river. You're trying to paddle upstream with everything you've got, Using the full speed of light, you're still moving relative to the water, but the current is already dragging you so fast that you're losing right at the event horizon. The flow of space-time itself reaches 186,000 miles per second. That's the speed of light. Light, our absolute champion swimmer, crosses that line. It's still moving forward, but the space around it is rushing toward the center of the black hole at the same speed. The light is doomed. It cannot swim back out. That's the horror of it. The event horizon is the place where the laws of speed turn into the laws of geography. All the directions that used to be a choice, north, south, back toward Earth, now merge into one inward. The radius of this boundary depends on the mass of the hole. If our own sun suddenly collapsed into a black hole, which thankfully it won't, this event horizon would be only about 3 miles across. But even our modest neighbor, the supermassive black hole at the center of the Milky Way, Sagittarius A, has a radius that spans millions of miles. And this hole weighs about 4.3 million times more than our sun. For us, watching from about 26,000 light years away, this black hole is just a dark spot in the fabric of the universe. We only see its terrifying footprint, the accretion disk, a white-hot, furious ring of gas and dust spiraling toward its death, heating up to millions of degrees and blasting out X-rays before disappearing forever beyond the point of no return. But if you were the one approaching that boundary, what would you feel? Nothing. That's the paradox. You wouldn't feel yourself crossing the event horizon. There's no drop, no sudden fall. It's more like realizing the treadmill you're running on can't be shut off anymore. The realization that every breath, every movement, every attempt to turn around is only helping carry you faster toward an absolute, unavoidable end. And that end, the singularity, is waiting in complete silence. We left you standing at the invisible boundary of the event horizon where time itself breaks. But before we move on and look at what happens once that boundary is crossed, we have to ask a deeper question. Where do these monsters come from? Black holes don't just pop out of nowhere. They are the final, most dramatic outcome of a process that begins quietly, out in the frozen, dark emptiness. Their parents are stars. Every form of life in the universe, every atom in your body, your home, the air you're breathing right now, was forged in the heart of a star. Stars are giant, incredibly complex machines, and their existence is an endless conflict that eventually leads either to the birth of immortal light or to absolute darkness, born in a cold cradle. Our story doesn't start with fire. It starts with cold. Picture a cosmic cradle. These are molecular clouds, nebulae that can stretch across thousands of light years. They are incredibly cold, just a few degrees above absolute zero, filled with dust and gas, mostly hydrogen and helium. On human scales, it's like a vast, shapeless cloud of dust hanging in total silence. That cloud can hold hundreds of thousands of times more mass than our sun, but that matter isn't just scattered randomly. Under the pull of gravity, it slowly, almost invisibly, begins to clump together. That's the first act of the drama. Gravity, the same force that keeps you on Earth and that crushes black holes into existence, starts its work. It slowly but relentlessly squeezes these pockets of gas. As each chunk of cloud contracts, it begins to heat up. To feel this heating, think about what happens when you inflate a tire. When you compress air, it gets warm. Now multiply that effect by billions of tons of matter. A collapse that lasts millions of years drives the temperature inside this forming core up to millions of degrees Fahrenheit. And when the core's temperature hits roughly 27 million degrees Fahrenheit, something miraculous happens. Nuclear fusion switches on. A star is born. The main phase of a star's life is called the main sequence. This is where the eternal conflict truly begins. The battle we'll call the fusion factory versus gravity. Think of a star as a gigantic, carefully calibrated engine. Gravity is the star's own weight, its built-in self-destruct instinct. It's trying to crush everything, to squeeze all its matter down into a single point. The star's mass, trillions and trillions of tons, presses inward, creating unbelievable, almost unimaginable pressure. The fusion factory is the opposing force. In the star's core, under that monstrous pressure, hydrogen atoms are forced to fuse into helium. This process of nuclear fusion releases a staggering amount of energy in the form of light and heat. That energy creates an enormous outward pressure. For billions of years, these two forces balance each other in a perfect but fragile equilibrium. The weight of roughly 4.4 quadrillion pounds, our sun, is held up by the energy released as atoms fuse. It's like holding a skyscraper above your head, not with muscles, but with pure, controlled energy. And here, inside this balance, lies the scientific problem. How long can this factory keep running? The answer to that question decides the star's fate, and it is the key to the birth of a black hole. The answer is simple. Everything depends on the starting mass. A star lives as long as it has fuel, hydrogen. The long-lived stars like our sun. Our sun is a mid-range star. It burns fuel efficiently, like a car with great gas mileage. It has about 5 billion years of life left, slowly consuming its hydrogen. The heavyweights, the future monsters. Now imagine a star 10, 20, or 50 times more massive than the sun. Yes, it has much more hydrogen, that's true, but its gravity, its weight, is also many times stronger. To fight back against that crushing inward pull, its fusion factory has to run in overdrive. It doesn't burn fuel carefully. It burns like someone poured gasoline straight onto the fire. If the sun is a slow-burning candle, these heavyweight stars are sticks of dynamite with very short fuses. They use up what would be billions of years' worth of fuel in just a few million years. Their lives are brilliant and incredibly short. Let's look inside this fusion factory in its final days. As a star with, say, 15 times the mass of the sun burns through its hydrogen, it starts to fight for its life. The core, stripped of hydrogen fuel, begins to contract. Gravity wins the first round. But that collapse, that rise in pressure, triggers a new, hotter stage of fusion. It's like a giant corporation on the brink of bankruptcy, selling off its assets to fund new, increasingly risky short-term projects. The star begins burning helium, turning it into carbon and oxygen. This fusion demands much higher temperatures. The energy it releases is more intense, but the phase is much shorter. The factory shifts into run until you break mode. Around the core, layers begin to build up like the rings of an onion. Hydrogen burns in the outer shell, beneath it helium, deeper still, carbon and oxygen. This chain of burning stages continues until the star reaches silicon. At that point, the core becomes a hellish reactor. For a star with about 25 solar masses, hydrogen burning takes millions of years. Helium burning takes hundreds of thousands of years. Carbon fusion lasts only a few hundred years. And burning silicon into iron, that final step, is a wild sprint that lasts just one day. This is the last desperate move. The star is like a sprinter who knows that at the finish line there's no medal, just a cliff. It throws everything it has left into the fire. And now we reach the moment when drama turns into tragedy. By the end of that insane day, the star's core has become a lump of iron. Iron is the most stable element in the entire universe. And from the star's point of view, it's a curse. When the star tries to fuse iron into heavier elements, it doesn't release energy, it absorbs it. Iron is the final border. At that moment, the fusion factory that fought gravity for millions of years finally betrays itself. It hasn't just stopped, it now needs energy from outside just to keep going. The outward pressure that was holding up the skyscraper vanishes. Gravity, which has been patiently waiting for its moment, gets a full green light. The weight of the entire star, billions and billions of tons, maybe 50 times the mass of our sun, starts to collapse. It doesn't fall inward slowly. It happens almost instantly. This isn't just an ending, it's an implosion. The whole star crashes down onto its iron core at speeds reaching up to a quarter of the speed of light. Having failed its final desperate test, the star is about to face the most brutal response imaginable. It's this catastrophic defeat in the fusion conflict that we'll explore next, when the balance breaks and the crisis begins. Our journey began with a catastrophe we saw coming. The core of a heavyweight star finally reached iron, the absolute dead end. The outward pressure vanished. Gravity, held in check for millions of years, now wins in an instant. The entire star, all of its matter, tens of times the mass of the sun, collapses inward. This collapse happens at a terrifying speed, reaching up to a quarter of the speed of light. It feels like this should immediately create a black hole, but the universe almost never follows simple rules. At the moment when all that infalling matter slams into the tiny, almost incompressible iron core, something else happens. A cosmic rebound, the epicenter of a supernova. All that mass rushing inward hits the core and bounces back out. A powerful shockwave rips through the collapsing layers, tearing them apart. This is a supernova, the most powerful, spectacular explosion you can even imagine. For a few weeks, this blast can shine brighter than an entire galaxy of hundreds of billions of stars. The energy, the light released in a fraction of a second, can travel millions of light years to reach our telescopes, telling us about a furious death that happened billions of years ago. But even this violent explosion isn't the most interesting part. The real shock is the mechanism behind it. When an entire star implodes, the gravitational energy released has no equal. In that instant of implosion, as matter is crushed to unimaginable extremes, something else is born, and it's crucial: neutrinos. Trillions upon trillions of these elusive, nearly massless particles are created as protons and electrons are forced to merge into neutrons. They blast out from the core at nearly the speed of light. The energy the star spent burning fuel over millions of years now pours out in a neutrino burst that lasts only a few seconds. That neutrino flash, invisible but all-penetrating, shoves the outer layers of the star outward, literally blowing them into space. And this explosion doesn't just scatter gas, it does something vital for us. A supernova is a cosmic forge. In that furnace, in that shock wave powered by neutrinos, the heaviest elements are made: gold, platinum, uranium. The elements inside your electronics, your jewelry, even the calcium in your bones, they were forged in that moment inside this cosmic meat grinder. The death of a star, in that sense, is not an ending. It's an act of creation. The light curve of a supernova has its own eerie drama. If you look at how its brightness changes over time, you're not just seeing a flash, you're seeing a story. First, a wild, uncontrolled rise, then a peak, so bright it can, for a few days, outshine half a galaxy, and then a slow, mournful fading that lasts for months. It's the light echo of a death. But the crisis in our story isn't the explosion itself. The crisis is what the explosion leaves behind. We are taught that if you throw something heavy into water, it sends out huge ripples. A supernova is the biggest, loudest stone the universe ever throws. But when the dust finally settles, when that unimaginable roar dies away, we often see something that doesn't match our expectations. We expected chaos, a boiling, shredded battlefield. Instead, we often see quiet, something small, cooling, incredibly compact. We see a white dwarf. For stars like our sun, this is the final, least dramatic chord. After its fusion factory shuts down for good, the sun will someday shed its outer layers of gas into space, creating a beautiful planetary nebula. What remains is an unbelievably dense core, about the size of Earth, but with the mass of the Sun. A mismatch you can feel. You were told the fire has burned out. You expect to see a pile of ash and an empty fire pit. Instead, you see a perfectly solid, glossy block of coal that weighs millions of tons, but gives off no heat and no light. That's a white dwarf. The burned out and gone model breaks here because this coal isn't just dead matter, it's still an active player. White dwarfs don't produce new energy. They simply cool slowly over billions of years. They're held up against further collapse, not by nuclear fire, but by a completely different, very strange force. And that force is the key to our crisis, the quantum dead end. Gravity wants to crush the white dwarf. The mass, think of that 4.4 quadrillion pounds, presses inward. Why doesn't the star keep collapsing? Why doesn't it become a black hole? The answer lives in a world that feels almost irrational to us, quantum mechanics. When matter is compressed to such extreme density, electrons, the particles that form the outer shells of atoms, end up packed so tightly together that they literally refuse to be pushed any closer. This isn't just particles bumping into each other like billiard balls. This is a quantum dead-end electron degeneracy pressure. Electrons are fermions, and they follow a rule you can phrase like this. Two electrons can't occupy the same quantum state in the same place at the same time. Imagine you're in a completely packed subway car at rush hour. You're trying to squeeze through the door, but every seat, every bit of standing space already has one person in it. If you try to sit where someone already is, the entire structure, the seat, the door, the car, pushes back. The harder you shove, the stronger the resistance. Electrons, cornered by gravity, refuse to be packed any tighter. They create an invisible but absolutely rigid support. Because of this electron degeneracy pressure, a single teaspoon of white dwarf material weighs several tons. The density is unimaginable, but it's stable, perfectly stable, the eternity of a white dwarf. To really feel the mismatch, you have to imagine the future of a white dwarf. This object, Earth-sized but sun-mass, will outlive almost everything else in the universe. It's a cosmic elder that can even outlast some black holes on certain timescales. Since it doesn't generate new energy, it just keeps cooling, slowly. That cooling will take quadrillions of years. That time span is so enormous that compared to it, the age of the universe, 13.8 billion years, looks like a short episode in a long-running show. When the cooling finally ends and the white dwarf no longer emits visible light, it becomes a black dwarf. By then, the entire cosmos will be dimming, expanding, drifting toward thermal death. But in that vast cosmic silence, these white dwarfs turned black dwarfs will keep floating through the void like dead frozen diamonds. They're a perfect, if boring, proof that you can survive after death. No explosion, no final scream, just quiet, inevitable cooling. The Chandrasekhar limit and the double crisis. So, where's the crisis? The crisis is that this quantum dead end has a limit. Indian astrophysicist Subramanian Chandrasekhar calculated that limit in the 1930s. When he was just 19, he showed that electron degeneracy pressure can hold up against gravity only as long as the white dwarf's mass stays below about 1.4 times the mass of our Sun. This threshold is known as the Chandrasekhar limit. Chandrasekhar's result didn't just trigger a scientific debate, it caused a full-blown crisis in astronomy. The famous British astronomer Sir Arthur Eddington refused to accept it. A champion of classical physics, he couldn't stand the idea that a young Indian theorist using quantum mechanics was predicting something impossible, the existence of such an extreme object. Imagine being a pillar of your field, and suddenly a student shows up and says your laws are incomplete. That for the most massive stars, death doesn't mean rest. It was a scientific rupture. Eddington mocked Chandrasekhar's idea, arguing that nature simply wouldn't allow a star to end its life in such an absurd way. But nature, as usual, turned out to be even more absurd. If a star ends up below 1.4 solar masses like our Sun, it quietly turns into a white dwarf and cools forever, beating gravity with quantum mechanics. That's the quiet fade-out ending. If a star's remnant exceeds 1.4 solar masses, the quantum dead end shatters. Gravity becomes so overwhelming that even electrons, those quantum fighters, can't stand against it anymore. They are forced to surrender. That's the mismatch. The burned out and gone model only works for about 97% of all stars in the universe. For the remaining 3% that cross that limit, the story gets much more extreme. Once a star passes this invisible threshold, electrons can no longer provide support. Under crushing gravity, they are literally forced to merge with protons in the core. To completely destroy the simplicity of burned out and gone, we have to look at the scenario of the double crisis. Imagine our white dwarf doesn't cool in silence. Imagine it has a companion, a nearby star that's still alive. This dead white dwarf, which was supposed to drift quietly through eternity, starts to steal matter from its neighbor. The stolen hydrogen and helium pile up on its surface, slowly increasing its mass, and so this perfect symbol of stability begins to creep past the Chandrasekhar limit. Instead of quietly collapsing the way a truly massive core would, this dead coal ignites in the brightest explosion the universe can offer, a Type 1a supernova. This time, the explosion isn't a core collapse event. It's a runaway thermal nuclear blast triggered in the outer layers of a dead, overloaded core. In a single moment, all the carbon in the core lights up. The star tears itself apart. Nothing is left but expanding gas. So we get two very different kinds of death that completely break the burn and fade model. A long, boring life that lasts quadrillions of years and ends as a black dwarf. A star that was already dead, which stages one final blinding firework, a Type 1a supernova, we use as a cosmic yardstick to measure distances. Both scenarios are a triumph of quantum mechanics over our desire for a simple story. But what happens when even the quantum dead end fails? What happens to the 3% of stars that cross the Chandrasekhar limit and never get the chance to become white dwarfs? What happens after electrons merge with protons is more than just death. It's the birth of true cosmic clocks and magnetic monsters, a turning point we'll explore next. We move from white dwarfs, quiet, boring remnants, to neutron stars, the densest, most exotic matter in the universe. We move from crisis to the breaking point. We left the universe in a state of defeat. Our simple burnout and fade model has collapsed, and the quantum laws that saved white dwarfs have failed in the face of the most massive 3% of stars. When gravity wins a total victory over the electrons, that's not the end, that's the turning point. The moment that leads to the birth of the most exotic objects in the universe. When a star crosses the Chandrasekhar limit, the 1.4 solar mass threshold, electrons can no longer resist. Gravity becomes so extreme that electrons and their proton partners are forced to merge, turning into neutrons. The entire atomic structure we know, a nucleus surrounded by orbiting electrons, is wiped out in an instant. Picture a cosmic collapse. A star that once stretched thousands of miles across suddenly shrinks at terrifying speed, down to the size of a medium-sized city about 12 miles across, roughly the length of Manhattan. This is a neutron star. That's the essence of the turning point. The death of a giant star doesn't lead to emptiness or quiet cooling. It leads to the birth of a new, exotic state of matter that doesn't obey any of the familiar rules. It's born out of maximum chaos and ends up as a pure example of absolute order. A core of neutron fluid. To understand the density of a neutron star, we need a new metaphor. Our old analogies for white dwarfs already felt impossible. An entire city block crushed into a sugar cube. That was shocking. Now we have to multiply that shock by 1,000,000. To reach the density inside a neutron star, you don't just compress a sugar cube, you would have to squeeze every car, truck, bus, and airplane on planet Earth into a volume no larger than a single raindrop. That's about 1,000,000,000 tons in a teaspoon. At this unimaginable density, matter behaves like nowhere else. The surface of a neutron star is incredibly smooth and hard, but just beneath that surface, the biggest paradox begins. Under this insane pressure, neutrons have no space left between them and form a superfluid, a liquid that flows with absolutely zero friction or resistance. In essence, the whole star is one gigantic atomic nucleus, blown up to cosmic scale, but its insides behave like the most perfect ghost-like fluid you can imagine. A neutron star is where the macroscopic world, a star the size of a city, and the quantum world, subatomic particles, fuse into one. Inside that 12-mile sphere, the density changes so sharply with depth that scientists gave its layers dramatic, almost sci-fi names. Imagine you're diving inward, outer crust, a rigid, frozen shell where atoms crushed to the limit form a crystal lattice. This is the surface you could theoretically stand on if gravity didn't crush you instantly. Inner crust, here the real drama begins. Neutrons start to drip out and escape, while the remaining protons and electrons that haven't yet merged assemble into bizarre structures, sheets, rods, tubes. Astrophysicists call this nuclear pasta. It is literally the strongest material in the universe, about 10 billion times stronger than steel. It's matter's final desperate architectural experiment before it gives up. Core. Down here, the density is so extreme that we can only guess. It may be quark matter, a state in which neutrons and protons dissolve into their most fundamental components. If that's true, then the core of a neutron star isn't just the death of matter as we know it. It's the birth of a new phase of existence that we cannot recreate in any Earth-based lab. Pulsars, cosmic clocks. This new object, the neutron star, is born with an enormous reserve of energy. It spins incredibly fast. When the original star collapses from a huge radius down to 12 miles, its rotation speeds up like a figure skater pulling in their arms. Neutron stars can spin hundreds of times per second. For comparison, a high-speed blender tops out at around 400 rotations per second, and the star keeps this up non-stop for millions of years. But the key twist is this: the collapsing star also concentrates its magnetic field. That field becomes monstrous, trillions of times stronger than Earth's magnetic field. When that immense magnetic field interacts with rapid rotation, it sends out narrow beams of radio waves into space like the beams from a lighthouse. If those beams sweep past Earth as the star spins, we detect perfectly regular, razor-precise pulses. That's a pulsar. Here's the twist. What should have been one of the most chaotic objects left after a supernova becomes one of the most orderly. The end of order creates the most perfect clock. Pulsars detected in 1967 were the first solid evidence that neutron stars actually exist. When Jocelyn Bell Burnell first recorded these pulses, she and her colleagues briefly thought they had caught a signal from an alien civilization. The pulses were so regular they looked artificial. It was one of the greatest false alarms in astronomy, and it led to one of its greatest discoveries: the precision of pulsars. Gravity detectors. These pulsars are more than just clocks. They are so precise that scientists use them to weigh the fabric of space-time itself. Think of using a stopwatch so accurate it would gain or lose 1 second only once every 10 million years. With that kind of precision, you can detect the tiniest disturbances. When a massive black hole or another neutron star passes somewhere nearby, it sends ripples through space-time, gravitational waves. Those waves slightly change the distance between us and the pulsar, and we can measure that as a tiny shift in the arrival time of its pulses. In this way, pulsars act as cosmic receivers for gravitational waves, ripples in space-time invisible to the eye. They prove that the fabric we travel through is not fixed, but constantly deformed by the weight of cosmic monsters, magnetars, absolute beasts, and the magnetic fist. Even among neutron stars, there are monsters. If the parent star wasn't just massive but also had an especially strong original magnetic field, the collapse produces a magnetar. This isn't just a strong magnetic field. It's a field a quadrillion times stronger than Earth's. This is the universe's magnetic fist. To feel that power, imagine living 1,000 miles from a magnetar. Even at that distance, its magnetic field would be strong enough to literally tear apart the molecules in your body. Your hair, your blood, your bones, everything would be stretched and distorted. Real magnetars sit tens of thousands of light years away from Earth. If one somehow appeared just 100,000 miles from us, very close by cosmic standards, it would rip every electron out of the atoms in your body. It would wipe the data off every credit card on the planet, even if they were locked in vaults. It would erase the chemistry of life itself. Magnetars suffer starquakes that rip through their crust. These aren't earthquakes, they are starquakes, shifts in the magnetar's crust that rearrange its magnetic field. Those fractures generate bursts of gamma rays and X-rays so powerful they can be seen from the far side of our galaxy. In 2004, astronomers detected such a flare from a magnetar that actually disturbed the upper layers of Earth's atmosphere, even though it was about 50,000 light years away. In a tiny fraction of a second, that event released more energy than our sun can produce in 250,000 years. That wasn't a direct hit. That was just the ripple of its cosmic punch, felt across tens of thousands of light years. It's proof that even far out in the galaxy, there are objects whose power can briefly, but instantly, alter our reality. The threshold of absolute density, the turning point, shows us that the death of a massive star doesn't lead to just two outcomes, but four extreme states of matter. From the quiet end, white dwarfs, to perfect clocks, pulsars, to the ultimate magnetic monster, magnetars. But we're not done with monsters yet. We have to return to our original question. What happens when even neutron resistance fails? Then we are back to the black hole. A neutron star is the last barrier. If the collapsing core is more than about 3 solar masses, gravity defeats not only the electrons but also the neutrons. There is no longer any force, no electron degeneracy, no neutron degeneracy, capable of stopping the collapse. All of that matter falls into an infinitely small point, the singularity. A neutron star is, in effect, the densest object that can exist before it becomes invisible. It's the upper limit of density that neither electrons nor neutrons can surpass, a limit with no return. These extreme objects, rapidly spinning pulsars and magnetars, and the massive black holes they sometimes fall into, shape the architecture of the entire cosmos. They are the main actors in the drama we call the universe. Their enormous power, locked into such tiny volumes, decides how galaxies form, collide, and move. We're stepping up to a new scale. We left our drama at the level of the densest matter in the universe, neutron stars. We watched how a star that crosses the 1.4 solar mass threshold collapses into an object as dense as anything can be, yet only the size of a small city. But even these objects, these cosmic monsters, don't exist in isolation. They're embedded in something much larger. To really understand their nature, we have to understand the architecture of their home, the universe. Our brains are wired to see the cosmos as random chaos, a huge box filled with scattered stars and galaxies. In reality, the universe, about 13.8 billion years old, is organized with an almost frightening efficiency. Imagine studying a painting while standing too close. All you see are individual brushstrokes, blobs of color, texture, but when you step back, a few million light years back, something monumental comes into view. Galaxies, cosmic cities. Every galaxy, whether it's our home, the Milky Way, or our nearest large neighbor, Andromeda, is a gigantic rotating city, held together by gravity. Our Milky Way alone holds roughly 400 billion stars. Galaxies aren't static cities. They evolve. The Milky Way is a bright, active, growing metropolis that's still under construction. Current estimates suggest there may be up to 2 trillion galaxies in the observable universe, but there are different types of galactic cities, and they tell us about the life cycle of cosmic structures. Elliptical galaxies are usually older, massive city-states that have finished their most active star-forming phase. They often form when 2 or more spiral galaxies collide and merge, leaving behind a giant, calmer remnant. That's our future. There are also irregular galaxies, small, chaotic places that look like cities thrown together on ruins with no clear plan. If the Milky Way is a huge, ancient, sprawling city, then Andromeda is an even larger, older megacity, just 2.5 million light-years away. And here, the reappraisal begins. These 2 cities, the biggest star collections in our neighborhood, aren't drifting apart, they're moving toward each other. At about 70 miles per second, that's fast enough to go from New York to Los Angeles in about 40 seconds. In roughly 4.5 billion years, these 2 giants will collide and merge, forming a new, more relaxed elliptical galaxy that astronomers already call Milkomeda. To us, the word collision sounds like catastrophe, but on the scale of galaxies, it's more like a cosmic waltz. Stars rarely hit each other, but their orbits are changed forever. It's more merger than destruction. Scale contrast. From star to city, to feel the true size of these cosmic cities, we have to revisit the largest single residence that can live inside them. We've talked about stars, but even the biggest ones that end as supernovae are tiny compared to the real giants. Take UY Scuti, a red supergiant whose radius is about 1,700 times that of our Sun. If we placed UY Scuti at the center of our solar system, its outer layers would swallow not just Mercury, Venus, and Earth, but also Mars and Jupiter. It would stretch to roughly halfway to Saturn. It's a lone monster. Now imagine this. That unimaginably huge star capable of swallowing entire planetary systems is just one of roughly 400 billion stars in the Milky Way. And the Milky Way is just one node in the cosmic web. That's the difference between a single grain of sand and an entire continent. Our place in the universe is not special and isolated. We're part of an endless crowd, quasars, ancient beacons, and the beginning of time. So what sits in the hearts of these galactic cities? We already know: supermassive black holes. In the young, violent universe, these black holes were hungry. They fed on gas so rapidly that the infalling matter shone with unimaginable brilliance. These were quasars, the brightest persistent objects in the universe. Quasars are beacons that let us look back into the earliest epochs. Their light has traveled across the expanding universe to reach us, and by studying it, we see what the cosmos looked like when it was very young. A quasar isn't just a bright spot. It's a visual comparison between our calm, aging universe and its wild, furious youth. The supermassive black hole at a quasar center can be billions of times the mass of the Sun. Quasars are proof that our black holes were once far more active and aggressive. Their light is so intense, it drowns out the combined light of billions of stars in their host galaxies. In a very real sense, quasars are our time machines. Looking at them, we don't see now. We see what was happening billions of years ago when the universe was a child. Black hole activity, the first picture. To close the loop of this reappraisal, We have to connect those ancient monsters to their quieter modern behavior. We already know there's a supermassive black hole called Sagittarius A at the center of our own galaxy. But to see how black holes shape their galaxies, we look next door. In April 2019, the Event Horizon Telescope, EHT, a global network of radio telescopes, acting together as one Earth-sized virtual dish, did something once thought impossible. It captured the first image of a supermassive black hole's shadow. The target was the black hole in galaxy M87. We didn't see the object itself, but its shadow cast against the glowing accretion disk, the superheated matter spiraling inward, emitting X-rays as it falls. That image is the proof of our entire drama. It shows that the monsters we have been talking about are real, and that the laws of physics really do break down at the event horizon, the cosmic web. Finally, we arrive at the grandest reappraisal. Our galaxy, our city, is not an island. It's built into something much larger. For a long time, we pictured galaxies as randomly scattered through space, like raisins in a loaf of bread. Modern observations show something very different. The universe has structure. That structure includes clusters of galaxies, superclusters, filaments, and voids, all woven together into a vast, intricate cosmic web. The roots of this web go back to the very beginning. The cosmic microwave background, CMB, the afterglow of the Big Bang, gives us a snapshot of the universe when it was just about 380,000 years old. In that faint glow, scientists found tiny fluctuations in density. Those were the seeds which, under gravity, grew over billions of years into galaxies and the entire cosmic web. Imagine the universe as a gigantic wet sponge, or even better, as a neural network scaled up beyond imagination. That's the cosmic web. Galaxies line up along filaments, strands of gas and dark matter. These filaments intersect at nodes, enormous clusters of galaxies that contain thousands of stellar cities. If you dried out a sponge, the water would drain away and collect where the sponge is thickest. In the same way, gravity pulled both normal and dark matter into these filaments, leaving behind vast empty regions. And here is the true essence of this reappraisal. Dark matter. Everything we've seen so far, black holes, neutron stars, the billions of stars, is just 5% of the universe's total matter and energy. That's normal matter. Another 27% is dark matter, an invisible substance that neither emits nor absorbs light. We infer its presence only through gravity, through the way it warps space-time around galaxies. Dark matter is the skeleton of the cosmic web. It's not the water in the sponge, it's the sponge's framework. This invisible, omnipresent structure dictates where galaxies form and how they move. Our cosmic cities are built according to rules set by an unseen architect. Clumps of dark matter form halos around every galaxy, holding them together like invisible glue. Without that glue, a galaxy spinning as fast as ours would simply fly apart under its own rotation. Our place in the universe. The Laniakea supercluster. To feel how deeply we're embedded in this structure, we have to look at our address on the cosmic map. The Milky Way belongs to the local group, which itself is part of the Virgo supercluster. But even the Virgo supercluster isn't the top level. It belongs to an even larger structure astronomers call the Laniakea supercluster, immeasurable heaven in Hawaiian. Our existence is not a random dot, it's a point in a gigantic hierarchical system. We're flowing along this network with trillions of other stars guided by the invisible gravity of dark matter. Voids, absolute emptiness and dark energy. Between the filaments of the cosmic web lie the voids. Voids are not just places with less stuff. They are actively expanding regions. At first, matter in the early universe was spread almost evenly, but gravity caused slightly denser regions to pull more mass toward themselves. Regions with slightly less matter lost it to their denser neighbors and gradually became emptier. Voids are enormous, empty bubbles that can span hundreds of millions of light years across. A way to feel it. Voids aren't holes in the fabric. They're bubbles that grow because gravity is constantly pulling matter out toward denser filaments. Voids are something you can't explain by looking at a single star or even a single galaxy. They force you to see the universe as one breathing organism. But voids matter not just because of what they lack. Many scientists believe they're the key to the biggest mystery of all: dark energy, which makes up the remaining 68% of the universe. Dark energy is an invisible something that drives the accelerated expansion of the universe. It was discovered in the late 1990s by studying distant supernovae. Voids, being the largest empty regions, expand the fastest. While gravity works to pull galaxies together into clusters, dark energy pushes them apart. Gravity versus dark energy is the greatest unresolved drama. Gravity, embodied in black holes and neutron stars, is trying to build order, to build cities. Dark energy, expressed in the growth of voids, is trying to rip them apart. It's a cosmic struggle between forces that build and forces that undo. This reappraisal inevitably pushes us toward the question of the end. What is the fate of this magnificent, fragile structure? If dark energy keeps dominating and continues to accelerate the expansion of the universe, we are headed toward the scenario called the Big Freeze, the heat death. Galaxies will drift so far apart that even our neighbor Andromeda will become unreachable. Stars will eventually burn out, and the universe will slowly turn into a cold, dark, almost lifeless place. In a less likely scenario known as the Big Rip, the repulsive effect of dark energy could grow so strong that it overcomes all other forces, gravity, electromagnetism, and literally tears apart galaxies, stars, planets, and even atoms. On this scale, we see that the monsters, black holes, sit at the centers of cities, galaxies, which are strung along filaments, the cosmic web, all floating inside expanding bubbles of voids inflated by an invisible force, dark energy. This structure ties everything together, from the instant collapse of a neutron star to the 4.5 billion years left before our galaxy collides with Andromeda. But that knowledge brings us to a new, deeper question. If we are nothing more than dust forged in supernovae, drifting along the strands of a cosmic web where 95% of our reality is invisible to us, what does that say about our ability to truly understand reality? We've spent a long time looking at objects. We've studied the bricks our cosmic house is built from. But now that we understand the scale of the structure, we have to turn away from the walls and look in the mirror. The question is no longer, what is this made of, but why is it made this way? And most importantly, why are we here to see it at all? This takes us into the most unsettling and profound part of our journey. We're stepping onto the border where astrophysics meets existential dread and maybe a higher kind of hope. The Anthropic Principle. Let's start with the fundamental laws. When we look closely at the physics of our universe, we find something strange. The constants of nature, the strength of gravity, the mass of the electron, the charge of the proton, seem suspiciously perfect. This is called fine-tuning. If gravity were just a fraction of a percent weaker, matter would never have clumped into stars and galaxies after the Big Bang. The universe would have stayed a cold, dark soup. If gravity were a bit stronger, the universe would have collapsed back into a singularity long before life had any chance to arise. The same goes for the nuclear forces. Tiny changes in carbon, the backbone of our biology, would never form inside stars. We exist on the edge of a razor. That leads us to the Anthropic Principle. There are two ways to look at it. The first is the weak Anthropic Principle. We see the universe this way because if it were any different, we wouldn't be here to see it. That's basically a tautology. True, but not satisfying. The strong Anthropic Principle goes further. It suggests that the universe, in some sense, must have properties that allow life to develop at some stage in its history. That's a disturbing idea. Does it mean the universe was made for us? Or more likely, from the point of view of modern cosmology, did we just win the most improbable lottery in the history of existence? The multiverse, an infinite landscape. To explain this absurd luck without reaching for mysticism, physicists turn to a concept that completely rewires our idea of reality: the multiverse. The idea is simple and dizzying. What if the Big Bang wasn't a one-time event? Cosmic inflation, the theory of ultra-rapid expansion in the first fractions of a second, suggests that this expansion might have been uneven. Think of boiling water. Little bubbles of steam pop up randomly. In that analogy, each bubble is a separate universe. We live in one such bubble, but far beyond our cosmic horizon, in an endlessly inflating foam, other bubbles may exist. And in each of them, the laws of physics could be completely different. In one universe, gravity is so strong it crushes everything instantly. In another, light crawls slowly. In a third, atoms can't bind at all. In this infinite landscape of possibilities, most universes would be dead, sterile wastelands. But with big enough numbers, at least one bubble has to get the settings just right. That's our bubble. We're not here because we're special. We're here because in an ocean of failed universes, one of them had to work. The music of reality. But what lies behind those laws? If we dive past atoms, past quarks, what do we find at the deepest level? Here comes string theory. It's an ambitious attempt to unify all forces of nature into a single theory of everything. It offers a radical idea: the fundamental building blocks of the universe aren't dots or particles, but tiny vibrating one-dimensional strings. Think of a guitar. One string can play many notes depending on how it vibrates. In the same way, according to string theory, an electron is one note, a quark is another, a photon is a third. All of reality, all matter and all forces becomes a cosmic symphony played on invisible strings. But there's a price. To let these strings vibrate the way they need to, our usual 3 dimensions of space and 1 of time aren't enough. The math demands more, 10 or even 11 dimensions. Where are they? We don't see them. String theory says they're compactified, curled up into incredibly tiny loops so small we'll never be able to probe them directly. But the shape of these curled up dimensions dictates how the strings vibrate, and therefore sets the physical laws of our universe. That means our visible universe is just a surface, a shadow of a far more complex, higher dimensional reality. The Drake equation. If the laws of physics allow for our existence, and if we live in a galaxy with 400 billion stars, a painful question follows. Where is everybody? In 1961, astrophysicist Frank Drake wrote down an equation to estimate the number of active, communicating civilizations in our galaxy. He broke the problem into factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets, the probability life will arise, the probability intelligence will evolve, and so on. Today, thanks to telescopes like Kepler, we know that most stars probably have planets. We know extremophiles can survive in hellish conditions on Earth, hinting that life is robust and adaptable. Even with conservative numbers plugged into Drake's equation, our galaxy should be buzzing with neighbors. The sky should hum with radio signal, but we hear nothing. That silence is more terrifying than any black hole. It suggests the existence of a great filter, some almost impassable barrier that stops life from reaching the interstellar stage. Maybe life starts often, but intelligence is an evolutionary fluke that happens only once in a billion years. Or maybe intelligence arises regularly, but technological civilizations always destroy themselves. Nuclear war, runaway AI, ecological collapse. The list of threats we've invented for ourselves in just the last 100 years is already frightening. If the great filter is behind us, then we are unbelievably rare and precious. We are the keepers of the flame of consciousness in a dead galaxy. If the great filter is ahead of us, then we may already be doomed, one more brief flare among countless others that burned out. The silence of the cosmos becomes a graveyard of civilizations that couldn't survive growing up. The illusion of reality, the holographic principle. But what if the stage for all this drama is itself not real in the way we think? What if space is an illusion? Studying black holes led physicists to one of the strangest ideas in modern science, the holographic principle. Remember Stephen Hawking and his work on black hole radiation. One key question was, what happens to information when something falls into a black hole? Does it disappear? Quantum mechanics says information cannot be destroyed. The proposed solution is that the information doesn't vanish. It's stored on the surface of the black hole on its event horizon. That sparked a radical thought. If all the information about a three-dimensional object, a star, a planet, an astronaut, that falls into a black hole can be fully encoded on a two-dimensional surface, maybe this rule applies to the entire universe. The holographic principle suggests that our entire three-dimensional reality, you, me, stars, galaxies, is a projection of data written on a distant two-dimensional boundary of the cosmos. Think of the hologram on a credit card. It's printed on a flat piece of plastic, but when light hits it, you see a three-dimensional image. We might be that image. We feel depth, we feel volume, but at the most fundamental level, we could be bits of information painted on the edge of the universe. If that's true, the line between reality and simulation begins to blur. We are mathematics, given the fabric of time and wormholes. If space might be an illusion, what about time? Einstein's general relativity tells us that space and time are woven together into space-time, a single fabric, and that fabric isn't rigid. It can curve, stretch, and even tear. In principle, that allows for the existence of wormholes, Einstein-Rosen bridges. These are tunnels connecting two distant points in space-time, creating shortcuts through the universe. Draw two dots on a sheet of paper. The shortest path is a straight line. But if you fold the paper until the dots touch, you can jump directly from one to the other. A wormhole does the same thing with the fabric of reality. We haven't found any wormholes, and keeping one open would require exotic matter with negative energy. But the fact that the equations allow them at all is enough to change the story. It means that distances we treat as absolute prison walls might be breakable. It means time travel isn't just fiction. It's a theoretical possibility hidden in the geometry of the universe. Time stops being a one-way river and becomes a landscape, one we might, under the right conditions, be able to move through. Heat death. But whether our universe is a hologram, a string symphony, or just one bubble in a cosmic foam, it has a direction, and that direction is pointing toward an end. The fate of the universe depends on the battle between gravity, which pulls everything together, and dark energy, which pushes everything apart. The data says dark energy is winning. The expansion of the universe is accelerated. That leads to the big freeze. The heat death. Over time, galaxies will move so far apart that their light will never reach each other. Stars will burn through their fuel and one by one go dark. New stars will stop forming as the last reserves of gas are used up. The universe will sink into eternal, cold night. Black holes will dominate this dark cosmos for a while, but even they aren't immortal. Through Hawking radiation, they'll slowly evaporate over trillions of years, eventually vanishing in brief flashes of particles. In the very end, only a thin, cold gas of photons and light particles will remain, drifting toward absolute zero. Entropy will reach its maximum. Time will lose its meaning because nothing will ever happen again. That's the quiet, frozen finale of the entire drama. There is another, more extreme option, the Big Rip. If dark energy grows stronger with time, it could eventually overcome all other forces, gravity, electromagnetism, and literally tear apart galaxy clusters, then galaxies, then solar systems, then planets, and finally atoms themselves, the universe would end in a moment of absolute disintegration, our answer to the abyss. All of this, the scenarios, the theories, the paradoxes, paints a picture of a universe utterly indifferent to us. It's too big, too old, too brutal to care. We are mold on a cooling rock, but right here, at the point of absolute nihilism, is where real meaning starts. If the universe has no built-in purpose, then we're not bound by anyone else's plan. If we are alone, then the responsibility is entirely ours. If no one is coming to save us, then we have to save ourselves. We are the way the universe becomes aware of itself. Without us or beings like us, the laws of physics would play out in darkness. No one would admire the beauty of a nebula or feel fear in front of a black hole's power. We give the universe scale because we're the only rulers that can measure it. Our fragility is not a flaw, it's our strength. Stars burn for billions of years, but they don't know they're burning. We live for a moment, and we know about eternity. We stand on the shore of the cosmic ocean. We have a choice. We can back away in fear from its depth and its cold, or we can build a ship. The knowledge we've gathered about strings, wormholes, dark energy, these are the blueprints for that ship. The great filter might be ahead of us, but we are the first species, as far as we know, that's aware it exists. Maybe that awareness is exactly the key to passing it. We are not just spectators. We are active participants in the evolution of matter itself, and our journey is only beginning. We've reached the very edge of what we understand. Behind us lies a 13.8 billion year story, written in the language of gravity, nuclear fire, and invisible matter. We've watched galactic cities rise from primordial chaos. Dying stars seed the cosmos with the elements of life, and black holes warp the very fabric of reality. But any good storyteller knows a story is defined not just by its beginning, but by its ending. And here at the brink of eternity, science slams into an unknown that is both terrifying and hypnotic. When we look into the future, we don't see guarantees. We see probabilities dictated by forces we've only just begun to understand. The main player in this final act is dark energy. This mysterious component, making up about 68% of the universe's total energy, currently sets the rules of the game. It drives space to expand, pushing galaxies farther and farther apart. And how this force behaves in the future will decide how our story ends. The most likely scenario predicted by current models is a long, slow fading, the big freeze or heat death. It's an ending without rage, an ending of absolute loneliness. Imagine looking up at the night sky billions of years from now. Dark energy keeps stretching space, and the galaxies we see in our telescopes today begin to slip beyond our cosmic horizon. They recede from us faster than the speed of light, and their light will never again reach Earth. Our observable world shrinks. Over time, even nearby galaxies disappear from view. The Milky Way, by then already merged with Andromeda into a giant elliptical galaxy, will stand alone in an endless black void. But that's only the beginning of the end. Stars are not eternal. The gas needed to form new ones will eventually run out. The last stars, long-lived red dwarfs, will smolder on for trillions of years. But even they will finally go dark. The universe will fall into permanent night. The only remaining engines of energy will be black holes. But they aren't immortal either. According to Stephen Hawking's theory, they slowly evaporate, radiating particles into the cold emptiness until they vanish in one final feeble burst. In this future, time itself starts to lose its meaning. When nothing happens anywhere, when entropy is maxed out and the temperature of the cosmos hovers just above absolute zero, there's no real difference between a second and a billion years. It's a quiet, frozen forever, a cemetery of infinite size, a monument to the fact that life once existed here. But the universe might choose a more violent exit. If the density of dark energy increases over time, it could turn into so-called phantom energy. In that scenario, the Big Rip, the expansion of space, grows so aggressive it overpowers all other forces. First, galaxy clusters are torn apart, then individual galaxies lose their stars. Next, dark energy reaches inside solar systems, ripping planets away from their suns. Earth, if it still exists by then, will be yanked out of orbit and flung into the dark. And the nightmare still isn't over. In the final instance, expansion outpaces the speed of light even on microscopic scales. The repulsive force becomes so extreme it overwhelms the electromagnetic forces that hold molecules and atoms together. Your body, rocks, air, everything is shredded into subatomic particles. The fabric of space-time itself is ripped to pieces. This isn't a quiet fade-out, it's a violent disintegration of reality, a sudden, absolute end to anything that has shape or structure. There's a third option, less favored by current data, but still theoretically possible: the Big Crunch. If gravity somehow manages to defeat dark energy and halt the expansion, the universe will reverse course and begin to contract. Galaxies will rush toward each other, the sky will grow not darker but blindingly bright, as the light of all stars is squeezed into a smaller volume. Temperatures will climb until stars begin exploding from sheer overheating. In the final moments, all matter, all energy, all space and time collapse back into a singularity, a point of infinite density and temperature, just like the one we think we started from. Maybe to trigger a new Big Bang and start the cycle over. Standing in front of these possibilities, we feel helpless. We look like hostages of physics, passengers on a sinking ship. But the human mind is not built to surrender without a fight. If space is a prison, maybe there are secret doors in its walls. Einstein's general relativity, the same theory that predicted black holes, also allows for another phenomenon: wormholes or Einstein-Rosen bridges. Picture the universe as a sheet of paper and you as an ant walking from one corner to another. The journey is long and dangerous, but if someone folds the sheet so that the two corners touch, you can make a single step and arrive instantly. A wormhole does that with space-time. It's a tunnel connecting two distant points, shortening the path through the cosmos. In theory, a wormhole could let us cross millions of light years in a moment, escape a dying galaxy for a younger one, or even, and here science brushes up against science fiction, travel through time. Right now, this is only a mathematical possibility. We have no idea how to create a wormhole. To keep its throat open and stop it from collapsing under its own weight, we'd need exotic matter with negative energy density, a substance we've never seen or held in our hands. But the fact that this possibility appears in Einstein's equations at all is enough to give us hope. It hints that the laws of physics are not our jailers. They're more like a complex code we haven't yet learned how to crack. And maybe our universe isn't the only stage. Cosmic inflation and string theory both push us toward the idea of a multiverse. The notion that our Big Bang was just one of countless bubbles boiling up in an eternal ocean of space changes everything. If that's true, the death of our universe is not the end of all things. It's just the closing of one chapter in an endless book. In this infinite foam of bubble universes, every possible version of physics is realized. Somewhere, gravity is too weak for matter to ever form stars. Somewhere else, nuclear forces are so strong that stars burn out in seconds. But in our bubble, thanks to an impossibly precise tuning of constants, we appeared. We are the eyes through which the multiverse looks at itself. And that brings us back to the most important question. Are we alone? The Drake equation, that attempt to estimate the number of civilizations in our galaxy, suggests we shouldn't be. There are billions of planets. Life is resilient, yet we hear only silence. That is the Fermi Paradox. That silence may be a warning. It may mean there is a great filter, a barrier that wipes out civilizations before they can make themselves known. Maybe that filter is self-destruction through technology. Maybe every civilization that discovers nuclear power or advanced AI eventually wipes itself out. If that's true, we are standing at the edge of a cliff, but there's another possibility. Maybe we're the first. Maybe we're the ones who made it through the filter of intelligent life, and now we face a vast, empty universe waiting for someone to claim it. We often search for meaning outside ourselves. We wait for a signal from aliens, a sign from a creator, or a final equation that explains everything. But what if the meaning isn't in what we find, but in who is doing the searching? We are the way the universe becomes self-aware. Stars are born and die in a blind cycle. Galaxies collide without emotion. But we feel, we understand, we fear, and we hope. We stand on the shore of the cosmic ocean, holding tools forged from the same stardust as our bodies. We've learned to see the invisible, to hear the whisper of gravity, to look back toward the beginning of time. As far as we know, we're the only beings who can predict their own extinction billions of years in advance and then seriously ask how to avoid it. Maybe our role in this vast, cold architecture isn't just to observe, but to act. Maybe life isn't just random mold on a rock, but the mechanism by which the universe tries to escape heat death. Maybe billions of years from now, a mind that began on Earth or on worlds we haven't found yet will learn to command stars, open wormholes, and rewrite the laws of physics to stretch existence further. The holographic principle hints that reality may be nothing like it appears. If our entire three-dimensional universe is a projection of data from a two-dimensional surface, then we are information, and information can be saved, copied, transmitted. That blurs the line between physical and digital, between matter and consciousness. We don't know what waits around the next bend. We don't know if we'll find life on Europa or Enceladus, if we'll unlock the secret of dark matter, or if we'll build a warp drive. But we do know one thing: we cannot stop. Curiosity is the gravity of our souls. It pulls us forward into the dark, toward new horizons. The universe is a locked room, and we've only just started feeling along the wall. But there is a door in this room, a door that hides answers to questions we haven't even learned to ask yet. Singularity, dark energy, consciousness, these are the key. And as long as we still have questions, the story isn't over. We are stardust that learned to speak, and as long as that voice is heard, the universe is alive. We are the bridge between beginning and end, between nothingness and eternity. And maybe that search, that endless attempt to understand the unthinkable, is our true home. We don't just live in the universe, we are the universe, and our journey is only beginning.